All right, let's talk about something that sounds like it's straight out of a sci-fi movie, but it's actually happening to you right this second. We're talking about gravitational time dilation. Yeah, it's a huge piece of Einstein's theory of general relativity, and we're going to unpack it.
So, let's just jump right in with a question that sounds, well, completely bonkers. Does your head age faster than your feet? Seriously.
And the answer, believe it or not, is yes, it does. Now hold on, before you start trying to walk on your hands to even things out, the effect is incredibly small. We're talking a few billionths of a second over your entire lifetime. But the fact that it happens at all, well, that tells us something absolutely profound about how time works.
Okay, so to understand why this happens, we have to kind of rewire our brains about a really weird fact about time. See, it turns out time isn't this constant, universal thing that just ticks away the same for everyone everywhere. It's relative. Here's a classic way to think about it. Imagine you've got two twins. One stays right here on Earth, while the other zips off on a super long journey into space, way, way away from Earth's gravity. When that space-traveling twin comes back, they'd find that their sibling on Earth has aged just a tiny bit less. Why? Because time itself actually slows down the closer you are to a big, massive object like a planet. The twin on Earth was deeper inside what we call a gravity well, so their personal clock, and yeah, their body's aging process, was literally ticking just a fraction slower.
And this whole idea has a name, of course. It's called gravitational time dilation. It's a real, measurable difference in how time flows for people at different distances from a source of gravity. The rule is simple. The closer you are, the slower time moves. So let's bring it back to you. Your feet are just a little bit closer to the center of the Earth than your head is, right? Well, that tiny, tiny difference in gravity is enough to make time tick at a different speed for both of them.
But that still leaves the biggest question, right? Why? Why on earth would gravity have anything to do with time? Well, to figure that out, we have to go back to a moment Albert Einstein had, a moment he called the happiest thought of his entire life.
So picture this. Einstein imagined a person falling off the roof of a building. Now, during that fall, for that brief, terrifying moment, they would be totally weightless. They wouldn't feel gravity's pull at all, just like an astronaut in space. And this simple thought, this realization, was the spark that connected two huge ideas, gravity and acceleration.
This is what led him to something called the principle of equivalence. And what it basically says is this. If you're in a small, closed-off space, like a windowless room, there is absolutely no experiment you could possibly do to tell whether you're sitting still on Earth or blasting through space in a rocket that's constantly accelerating.
And this image shows it perfectly. On one side, you've got someone just standing in a room on Earth feeling normal gravity. On the other side, you've got someone in a rocket ship accelerating upwards. From inside those rooms with no windows, there is literally no way to tell which is which. If you drop an apple, it's going to fall to the floor in exactly the same way in both scenarios. As far as you're concerned, the physics inside are identical.
Okay, so if gravity and acceleration feel exactly the same, well, that means that whatever weird effects acceleration has on reality, gravity must have them too. This is the key. It lets us do a little thought experiment in a rocket to figure out what's really going on with time.
All right, stick with me here. Imagine there's a light on the ceiling of that accelerating rocket, and it's sending out a little pulse of light every second. A pulse leaves the ceiling and starts heading for the floor. But remember, the rocket is accelerating upwards, so while the light is traveling, the floor is actually rushing up to meet it. That means the light's journey gets cut short, and it gets crazier. By the time the next pulse of light is sent, the rocket's moving even faster, so the floor rushes up to meet that second pulse even quicker.
So what's the result of all this? The light pulses actually arrive at the floor more often than they were sent from the ceiling. If you were standing on the floor, it would look like the clock on the ceiling was ticking way too fast.
And now, here's the mind-blowing leap. Remember the principle of equivalence? If this happens in an accelerating rocket, it has to happen in a gravitational field too. Think about a house on Earth. The ceiling is higher up in the gravitational field, and the floor is lower down.
So, we're left with this absolutely stunning conclusion. The only way for those light pulses to arrive at the floor more frequently is if time itself is passing more slowly for the floor than it is for the ceiling. The deeper you are in gravity's pull, the slower the clock of reality itself is ticking.
I know. That is a really tricky concept to wrap your head around. So let's try to visualize it a different way, with something called a light clock.
Okay, a light clock is super simple in concept.
Just picture a single particle of light, a photon, bouncing perfectly between two mirrors. Every time it hits a mirror, we'll say that's one tick of our clock. Got it? Cool. Now let's see what gravity does to this clock.
And this visual just nails it. On the left, in low gravity, the photon travels in a nice, short, straight line. Tick-tock, tick-tock, the clock runs fast. But on the right, in high gravity, we know that gravity actually bends the path of light. So now that poor little photon has to travel a longer, curved path to get from one mirror to the other. And since the speed of light never changes, it's the universal speed limit, a longer path means it takes more time. The clock ticks slower. It's as simple as that.
But here's the thing. This isn't just a clever thought experiment or a neat analogy. The slowing of time is not some kind of illusion. It's pointing to the fundamental truth of our universe. Gravity literally changes the fabric of reality.
You see, gravitational time dilation is real. Physical proof that massive things don't just create a force we call gravity, they actually warp and bend the very fabric of space-time. That's the 4 dimensions of reality, 3 of space and 1 of time. Everything we see moving, even a beam of light, is just following the straightest possible path it can through this curved, warped landscape.
The physicist John Archibald Wheeler summed up this entire incredible idea more beautifully than I ever could. He said, "Space-time tells matter how to move, matter tells space-time how to curve." It's like this incredible cosmic dance, where the dancers are actually shaping the dance floor as they move.
So we come all the way back to the beginning. The simple fact that your head ages faster than your feet isn't just some weird party trivia, it's a constant personal reminder that you are living in this wild, dynamic, relativistic universe. And it kind of makes you wonder, right? If something as fundamental as time can be bent and stretched by gravity, what else about our reality isn't nearly as solid as we think it is?